Hi everybody, my name is Jacob Tomlinson and I wanted to try something a little bit different. So I'm gonna be, over like the next month, I'm gonna be streaming, working through the advent of code, but I'm gonna try doing it on the GPU, right? So I work for NVIDIA. I'm a software engineer. I'm like a Python open source software developer. So I spend a lot of my time working on projects like Dask and Rapids, helping folks, deploy onto GPUs, make use of lots of GPUs in big clusters. Maybe they have Kubernetes with GPUs, or maybe they have access to some cloud platforms that they can get GPUs from, right? So I spend a lot of time working with GPUs, but I actually don't spend a lot of time writing code specifically for GPUs. I kind of do the stuff around the edges for deployments and setting things up. So I thought this would be like a good opportunity. I quite like doing advent of code anyway. I thought this would be a fun opportunity to try and bring up my ability of writing code for the GPU and share with others, and hopefully get people kind of coming and helping along. So hey, Samantha, sorry, my chat is like on a wrong color background, so it doesn't look very good over there. But yes, hi, welcome. So I'm going to be basically working through the advent of code. I'm going to do it in Jupyter. I'm going to be using Number, and hopefully going to be learning a bit about how to write code for GPUs. So I've got a Git repo set up here. I'm trying to kind of keep some questions in here and information if people pop into the stream and want to ask some questions. I've got kind of some stuff going on here to answer some of those. I will kind of keep it up to date as I'm going through. I'm also going to store my solutions in here, but I'm going to do everything in Jupyter. So what I have kind of already set up, I have a workstation desktop with some NVIDIA GPUs in, and already running on here I have the Rapids Docker image. So let me just have a look and show you rapids.ai. It's just there. I should click it. Right. I have so I work on Rapids. Rapids is a collection of GPU Python libraries, which have got some like accelerated C++ backends, but it kind of exposes it all in Python in a way that's familiar to folks that know libraries like NumPy and Pandas and that kind of stuff. One of the things that Rapids provides is like ways to get up and running, because all the NVIDIA libraries need drivers and they need certain things to be installed, and you can install all of that with Python and things. But one of the things you can do is you can go in and you can select a release, and then you can choose Docker, and you can get a Docker image and get Rapids with all the packages, and you can choose whatever base and that you would prefer. But I've basically done this right on my workstation. I've pulled down one of these runtime images, and I've run it, and it starts up Jupyter Lab, and it starts up Dask and these kind of things. Might not actually get to Dask in this. It depends kind of how hard these problems are. But the main thing it gives me, right, is this Jupyter Lab session on my workstation. I've made myself a new folder, which is this repo. I've put this in here, and I'm just going to try working through the advent of code problems. So let's talk a little bit about advent of code. Advent of code is like this nice challenge that goes up every December, where they have like a problem every day up until Christmas, and each problem is like I think it's based on like a reasonably classic computer science problem. I don't have like a computer science degree or anything, but I quite enjoy these kind of challenges. I'm a professional software developer. I like working through these things, so it's nice to kind of have a look through. We have a question. Should regular users and mortals care what CUDA version the Docker image uses? Yes. So on your machine, right, on my workstation, let me just open a terminal in here. If I run NVIDIA SMI, which shows me like what I have in terms of GPU setup, I can see I've got a couple of Quadro GPUs in here, but you can also see, my NVIDIA driver version is this, and my CUDA version is this. So this is kind of whatever the NVIDIA driver has given me. I think I've just installed, this is, the machine's running Ubuntu, like the base machine is running Ubuntu. So I've just used the Ubuntu drivers package to install the latest NVIDIA driver, and it's given me CUDA 11, so I chose the CUDA 11 image from here, right? But it's kind of, I think your CUDA version has to be higher than, like the CUDA version that you use in the Docker image has to be at least higher than what you have installed on the machine. But I think it's probably best to just match whatever, so, on your machine, if you run NVIDIA SMI, then match it, basically. Let's clear that out. So yeah, these are the kind of questions like I'm super keen to chat about, because I didn't know all of this stuff, but you know, until I joined Nvidia, and even now, like I often don't have to care about this stuff. So I just thought it'd be fun to kind of work through here. So yeah, advent of code, they're fun programming problems. I find it useful because I don't have like a education background in computer science. I like to try and top up my knowledge of these kind of standard patterns to you know, just help me out in work. So I enjoy doing these kind of things. What I like working through books and stuff that have got these kind of programming problems in. So we're going to work through advent of code. I'm going to try doing stuff on the GPU. The last like piece of this puzzle I guess I want to talk about is number. So if I just search number CUDA. So CUDA is like a C++ extension for writing GPU specific code. But there's a nice Python package called number, which does some like cross compiling of Python code. And number's great because it basically lets you write Python and then run that Python on the GPU. It also, you know, does CPU acceleration as well, but we can write some CUDA specific stuff. So number is like one of the building blocks of Rapids. So the fact that I've got I'm using the Rapids Docker image, I've got like loads of libraries in here, and one of those will be number already. We might use some other things, but who knows. So let's have a quick look through this documentation. So I've done like I did a talk on this for JupyterCon of how to like use GPU type stuff in JupyterLab. And I also did a talk at TechExtra this year of like an intro to development in like Python development in stuff. So like I've been through the basics. I've kind of been through it enough to give a talk about it because, you know, it's my job and I like to tell people how cool this stuff is, but I don't use it on a day-to-day basis. So this is going to be me refreshing my memory, reminding myself what's going on, and hopefully learning some stuff. So we've got CUDA installed. I've also got JupyterLab installed. This is the JupyterLab that came in the Docker image. And this JupyterLab has got a couple of extensions installed. It's got the Dask extension. Again, I don't know if we're going to get onto Dask and stuff. As I showed in my little NVIDIA SMI command before, I do have 2 GPUs in this machine, so I could use Dask to make use of both of those GPUs in like a single calculation. But for now, I'm just going to stick to single GPU stuff. So the other thing that I have here is the MV dashboard. So this is like a set of plots for seeing what your GPUs are doing. This is really helpful if you're in like a Jupyter environment. Let's open some up. Let's have GPU utilization, GPU memory. That'll do actually. I think I'm just going to open those two, collapse them down here a bit. So this is kind of showing me, this is like, you know, 0 to 100% of how busy my GPUs are, and then this is, you know, 0 to 48 gig or whatever my GPUs have got. These are, you know, reasonably high-end GPUs that I have access to here. But I'm going to kind of keep this open so I can see. I mainly just want to make sure I'm doing stuff on the GPU. So let's open that up. Let's go into solutions. I made a folder already for today, day 1. And then, I don't want the launcher again. Let's make a new notebook. So this is where I'm going to do everything basically. I'm just going to do a markdown cell and just say day 1. And let's just call this notebook, call it solution. Yeah, I call my notebook solution. I'm just going to quickly open up my Twitch dashboard just so I can see stuff on here. How do I make that go away? Chat. Right, I'm going to just put that there so I can see it. Don't know why that chat's not doing anything. I should, right, let me just mess about with my streaming setup a bit so I can see these chats. So let me, sorry, things get a bit funny, but let me add chat background. Sorry, I don't mean to do this like live. I tried to get myself all set up before, but let me just move that down to here. And then, there we go. Oh, I can see. Hooray. Okay, Fabio, feeling Christmassy already. Hey, Fabio. Yeah, so yeah, this isn't an advent of code for GPUs. This is just me fumbling around trying to do it on a GPU. And trying to learn a bit in the process about how to do this kind of stuff. So, okay. that's kind of slightly in the way, but I'll figure this out as I go along. So I'm going to do day one solution. So advent of code, day one. Sometimes I'm like really specific. Oh, you can't see that, can you? Let me. That's not a great layout, is it? Really? Because my head's in the way and the chat's in the way. I'm going to move the chat over here, I think. Chat over there. Okay, right. Hopefully that's me done faffing around with that. Right, let me read this out. So, day one, report repair. After saving Christmas 5 years in a row, you've decided to take a vacation at a nice resort on a tropical island. Surely Christmas will go on without you. Tropical Island has its own currency and is entirely cash only. The gold coins used there have a little picture of a starfish. The locals just call them stars. Okay, yeah, because Advent of Code is all about stars. None of the currency exchanges seem to have heard of them, but somehow you need to find 50 of these coins by the time you arrive so you can pay a deposit on your room. To save your vacation, you need to get all 50 stars by December 25th. Okay, so there's 25 puzzles. Each puzzle has like 2 halves to it, right? So I guess we have to solve all that. Collect stars by solving puzzles. 2 puzzles will be made available on each day in the Advent calendar. The second puzzle is unlocked when you complete the first. Each puzzle grants 1 gold star. Lovely. Good luck. Before you leave, the elves in accounting just need you to fix your expense report, your puzzle input. Apparently, something isn't quite adding up. Specifically, they need you to find 2 entries that sum to 2020 and then multiply those 2 numbers together. For example, suppose your expense report contained the following. Here's some numbers. In this case, the 2 entries that sum to 2020 are 1721 and 299. Multiplying them together produces that number. So the correct answer is that number. Of course, your expense report is much larger. Find the 2 entries that sum to 2020. What do you get if you multiply them together? Right. I'm still in the way of the puzzle and stuff, but that's fine. I've read that out. Sorry, I can think about how to rearrange things a bit. So there's a button behind my head called Get Your Puzzle Input. Ooh, that was not what I meant to do. But there it is. If I go like this, you can see, right? Get your puzzle input. So if I click Get My Puzzle Input, I just have a big input. So the first thing I tend to do is come in here and make a new file, and we'll call it, let's just call it input. We might need a second one of these in a second. And then let's copy content of that and just put it into this file. Right. Input.txt. So that's my input. I need to figure out which of them multiply together to make 2020. But I specifically want to do this with number. So let's kind of dive a little bit into some GPU type stuff. So in number, there's a thing called CUDA kernels, right? And a CUDA kernel is basically a function that you run on the GPU, right? Kernel is just like a fancy word for function here in this context. So you write a function, and then that function you decorate with CUDA.jit, and this is what tells number that, oh, this is a special function. It needs compiling into something that can run on the GPU. And then also the way that it's executed is slightly differently. It's slightly different. I think actually in my FAQ I'm going to put a link to the talk that I gave at TechExter, because I think this like covers a ton of this stuff, and I probably need to remember it myself, which is fine. But the GPU, I think you can think of as like a completely separate like thing, right? It's a completely separate computer almost. It's got its own processor. The processor works a bit differently. It's got its own memory. It's kind of got its own network connections, in that it connects to your machine via PCI, right? If you build a PC, you get a motherboard, you put a CPU in the CPU slot, and the GPU plugs into a PCI Express slot. And that PCI is kind of like a network connection inside the machine, in that you have to talk between the CPU, which is kind of where you do everything, right? By default, everything is on the CPU. If you want to do stuff on the GPU, you need to talk to it via PCI. and you need to like move stuff. You have like 2 lots of RAM that you have to worry about now. You have like your machine's RAM and the GPU's RAM, and so you have to copy stuff back and forth, move stuff around. Now Number will like handle a bunch of this stuff for us, which is really handy. But the way that the execution model works, which is kind of what we need to like rethink about in terms of doing this on the GPU, is on a CPU you call a function and it calls that function, right? Obviously that makes sense, right? You call a function and that function runs once on the CPU. If you want it to run multiple times, you do like a for loop or something and it calls that function over and over. Whereas on a GPU you have this idea of a grid and blocks and threads, right? Which is takes a little while to get your head around, but what it basically means is I'm going to call this function, but I'm going to call it lots of times at the same time, and the GPU is going to handle like doing all of this stuff in parallel because it is a parallel processor. And you can be very specific about how you call your code and how, you know, the dimensions of it, right? You're almost like creating an array of function calls, and like the useful thing here is each function is able to work out which function it is, right? If I call my function 1,000 times, that'll happen all in one go, but each function will go, oh, I'm number 1, I'm number 72, I'm number 436, like whatever. Like each function knows which one it is, which means it can do something different, right? It can follow different logic. They don't have to be like completely in lockstep. And when you call a CUDA kernel, they'll all execute at the same time, and they will only all finish when the last one finishes, right? So if you have like, you know, all of them do the same thing except number 672, which does something else which takes much longer, the whole GPU is just sat around waiting for that one thread to do that thing. So it's best to like not have the functionality like branching and deviating like too much. But it's you can have them do slightly different things, and the main way that you have them do slightly different things is you have them read different bits of memory. So let's have a first look at our input, right? We just have this list. We have this, it's not that long, right? It's 200 lines, but we have this like longish list, and I assume the next list we're going to get is going to be longer. So what you could do is we load this into memory somehow. We'll do that in a minute, right? But we could load this into memory. Then we can move it onto the GPU, and we'll worry about doing that in a minute as well. And then when it's on the GPU, we could call this function 200 times, right? We could write a function that deals with one number at a time, basically. But we call the function 200 times, and you know, the first one would go, oh, I'm number 1, so I'm going to take this, and I'm going to try adding all the other numbers to it. And then, you know, number 2 is going to take this one and try adding all the other numbers to it. We could do that. We could also be even more clever and be like, well, there's, you know, 200 things in this list, so we have, you know, 200 to the power of 200 various options that we can run through. And so we could be even more clever with it. But what I think we should probably do in this first solution is read the data in. We have to just do some basic reading into an array, put that array on the GPU, and then we'll write a little function which will take each number and try and work out whether it like has a pair of numbers to get to the 2020, because that's what we need to work out, right? Is that the two entries here, you see the highlighting? Yeah. Find 2 entries that sum to 2020 and then multiply them together. So let's start just copying some code from the number documentation. Is there like a really simple little example that I can copy from here? Examples. Matrix multiplication. Fine, I just want like the layout of this basically. So let me just remind myself what's going on. So I'm going to import from number. Let's import CUDA. That's like a good first step. And I've got this example here. All right, from number import CUDA. Now I can write my kernel. So this is, you know, I've got a function. Let's actually just delete most of this and that doc string as well. And we're going to take in something. Let's have a look at what I'm trying to do. That example isn't quite what I was aiming for. Let's come and have a Google of this. Let's just have number CUDA example. What's something really basic? Yeah, okay. Right, I'm gonna just copy some chunks from here. Let me actually, I'm just gonna, sorry about the swipey screening, but I'm just going to have a quick look and see if I have my example from TechExter, because that might be helpful actually. I'm just digging through some other files that you can't see. Project / I'll put it in there. No, it might be. What happens when I don't sort stuff so well? Yeah, no. Thought I found it, didn't. Number. Right. Okay, I'm gonna give up on that quickly. Let's just copy these examples from the documentation. We'll work through from the beginning together. Probably the best thing to do, right? So let's not worry too much about the advent of code for a second. Let's just work through doing some CUDA stuff with number. So what we're going to do, let me read this to you. So a kernel function is a GPU function that is meant to be called from the CPU. And it gives two fundamental characteristics. Kernels can't explicitly return, right? Because we're calling these functions completely in parallel, like getting a return value back out of them doesn't necessarily make sense. So what you do instead is you call a function and you generally give it like an input array and an output array. And they're like, they're basically pointers to lists or arrays or whatever that already exist. And then each kernel, when it's executed, it changes what's in the array. So instead of returning anything, it's almost a bit like a side effect, which is generally bad in Python, but it's got like this side effect of it changes what's in the array. And so instead of returning, you like have a look at the output array. Yeah, exactly. I think that's, I didn't read that example like super in depth, but yes, I think that is the idea, right? You take array A and array B and you multiply them together and you get array C out the end, but like there's no return in there. And then also kernels explicitly declare their thread hierarchy, which I don't understand this hugely well. I feel like every time I have to explain this, I like sit down and learn how it works and then tend to butcher it when I explain it to people. But this is what I meant about you kind of say, well, I want this function to be called 1,000 times, or you do it in like 2D or 3D arrays. So you say, I want this to be called 10 by 10 times, right? So 100 times, but in like a 10 by 10 block. You can do it in 1D, 2D, and 3D, I think, just because of the way that the CUDA libraries work. And that makes sense. Like if you're working with 1D, 2D, or 3D problems, it makes sense to call your function in 1D, 2D, or 3D layouts because it might map onto your problem a bit more. So we're not going to worry like hugely about this because I think we're going to have reasonably straightforward problems in terms of advent of code, but this is like a fun thing to work through. So yeah, I've copied this example across. Right, and then the kernel invocation is like this. So let me put this in another cell. So here we're specifying threads per block is 32. Blocks per grid is the size of an array plus threads per block divided by threads per block. So you're kind of saying, how big is my input? Oh, you can't see my, you can't see my GPU memory plot now. I'll get slightly distracted, but let's put my, let's open this one, which is got an error because I haven't got it set up properly, but if I go like that, then you can see these plots like that. Okay. So we want to work out like how many blocks per grid we're going to have. So the grid is like the high level object, blocks are the lower level object, and then threads are the like individual calls inside that. So blocks per grid is going to be however big your array is, basically divided by the threads per block. And then the way this gets called is in like two pieces here. So let's actually break this out. So we have our function here, our increment by one function, which doesn't have any code yet, but instead of calling this function straight away, we have to like initialize it. So let's do this in two steps. Let's do like initialized initted increment by one, and then we'll go like that. So you call your function but with square brackets, and you say this is the number of blocks per grid and this is the number of threads per block. So we've kind of already worked this out here, and this is kind of setting up our kernel. So we're saying, you know, here's our function, and now we're saying here's how we want to call our function in however many dimensions we're going to call it in. And then once we've initialized our function, we can then call it. And this is just like an extra step that has to be done for GPU things. But often you'll see the syntax like this, where it's kind of all done in one go. You have your function, you initialize it with your square brackets, and then you call it like immediately. So yeah, we have to instantiate, yeah, rather than do that. But then running it is just like calling a function. Now, yeah, it might seem curious to have a two-level hierarchy when declaring the number of threads needed by a kernel. The block size, i.e. the number of threads per block, is often crucial. On the software size, the block size determines how many threads share a given area of shared memory. On the hardware size, the block size must be large enough for full occupation of the execution units. Have a look at the CUDA-C programming guide, which is you know, very helpful and big and dense bit of documentation on how to do this stuff. But basically here we're saying when a block is executed, all of the threads inside the block have like a bit of shared memory. So you can do some clever stuff where they're kind of all communicating through some shared memory there. But also you want to keep the block size big so that you fully utilize the GPU. So the GPU at a hardware level is like broken down into these streaming multiprocessors, which take in like these blocks of calls and call them in parallel. And so if your GPU has they have this like idea of warps as well, which is like the number of things that are executed at once actually at the hardware level. So say your GPU has got like a warp size of 1024 or something. You need to give it 1024 things to do, otherwise, because that's like the smallest unit of stuff that it can do it in one go. So you need to give it enough work that it can do it all in parallel. If you just drip feed it little bits of function calls, it will do them, but it won't like fully utilize all of the silicon basically. So you have to like balance these things. I think somewhere in this documentation it kind of said like these numbers matter, but there's like there's not necessarily like a rule of thumb for working it out. So you kind of have to figure it out, right? So multi-dimensional blocks and grids. I'm going to keep reading this documentation because I think this is useful. So to help deal with multi-dimensional arrays, CUDA allows you to specify multi-dimensional blocks and grids, which is kind of what I was saying before, right? In the example above, you can make blocks per grid and threads per block tuples of 1, 2, or 3 integers, right? This is how you specify I want a 1, 2, or 3D block and grid. It doesn't actually change anything, right? Compared to 1D declarations of equivalent sizes, this doesn't change anything to the efficiency or behavior of generated code, but it can help you write your algorithms in a more natural way. So if you're trying to work, iterate over some 3-dimensional data, it might make sense to call the function in a 3-dimensional layout. And it's mainly because I was saying before, okay, I'm getting ahead. Let's keep reading. Thread positioning. When running a kernel, the kernel's function code is executed by every thread once. It therefore has to know which thread it's in order to know which array elements it's responsible for. One way to determine its position is manually compute the corresponding array position. So we can do things where we can say, what is my thread ID? What is my block ID? and how wide is this block, and then I can flatten that and work out like what is my position in the array, right? So this is what I was saying. Each function knows which function it is within this thread block. So let's copy this. Oh, and you can also just get absolute position, right? So you can get all of these things out, but you can also get just grid size. Okay, so you can, if we're working in a 1D array, which we will be for this problem, you can do something like say, my position is, you know, what is my position is what this is saying, and it will say, oh, your thread number 1, your thread number 101, and then you can say if the position is actually inside the array, right? If you have an array of 100 items and you call your function with 1,000 threads, 900 of those threads are going to have nothing to do. So you do need to do a bit of logic here to check, do I need to do anything? Am I one of these? So you say if my position is actually in the array, increment by 1. Okay, so this is our actual very simple thing. So let's do this here. So we're going to say increment by 1. We take in an array, and you work out your position, and then if your position is in the array, so if pos is less than the size of the array, then take the number in the array and add 1 to it. And then I think there's yeah, so let's call this with an array. Let me just try and remember. Yeah, okay, I want to use NumPy. So let's also import NumPy. Import NumPy as MP. We've got our increment by 1 function here, and I'm also going to do my input here array is 10 numbers. Right, let's have a look at it. This is an array of 0 through 9. I'm just using NumPy to arrange this layout. What I could do is do 32 threads per block, just because that's what it's kind of given me. I might actually just do that in a separate call, and let's say input array. Yeah. So let's print these out as well. I'm kind of trying to do this in small pieces, partly just to check my understanding, right? But threads per block is 32. Just make sure that's true. And then blocks per grid is 1, because 10. Let's make this 100. Okay, we have 100 numbers in an array. Now, if I have a look at this, I have 32 threads per block, and we need 4 blocks to get over our whole array. So that's what we're going to submit to the GPU. Is we're going to call our function. I deleted my invocation thing, didn't I? Let's come here. So in order to get over that, we've got our array size, and then I can increment by 1, and we give it the blocks per grid and threads per block, and then we're going to give it our input array. If I call this now, I don't know if you caught it, but my GPU did something, like a little bit of something happened up in the top corner. And this is because we called our GPU function, and it ran some code on the GPU. So it's not giving me any output, because like I said, these kernels don't return anything. So we've just incremented by 1 in this layout over our input array. You could do, these numbers are kind of whatever you want. So if we put 32 threads per block, I could put like 100 in here. It will call it of that size. It's just that loads of it is unnecessary. So all we're doing with these numbers is trying to work out what's the minimum amount of calls that CUDA needs to make to work over all of this. So if I now have a look at this, because this is modified in place, right? We haven't taken in like an input and an output. We've just taken in our one array. We've gone over the whole array, and we've incremented it by 1. So if we have a look at the input array now, all of these numbers have been incremented by 1. We've got, now this was a 0 counted array before. Now it's a 1 counted array, and we could do it again. And then if I have a look at the input array, it should now be like a 2 counted array. So we're starting from 2, right? So it's executing over all these numbers, and it's calling this function on every single one of them separately. you know, we could do some other stuff to kind of play around with this. So let's just say like get pos. I'm gonna probably just put some titles in and tidy this up in a bit, but let's have a new function, and all we're gonna do, we're gonna call this get pos. We're gonna take in an array, and we're gonna get the position, and then we're just gonna say this array's position is this, right? So all we're doing is we're gonna take something in and return it. So let's have a new input array, and let's call it pos array, and we're gonna do mp.zeros and 100 of them, right? What this will do is it will give me 100 zeros in an array in NumPy. Now what I'm going to do is I might encapsulate this. I'm gonna think of like a neat way of tidying it. No, it doesn't matter. Okay, I'm going to do threads per, I'm just going to copy these lumps again. So we've got threads per block and blocks per grid, and I'm just going to keep copying this section because it's useful to have it around. But this is going to be for our pos array, right? So we've got threads per block and blocks per grid for our position array. And then I'm going to call get position with our dimensions of our position array. Okay, now if I have a look at my position array again, it's gone and filled in these numbers, right? Yeah, that's a really good question. The array itself remains a NumPy array after the entire time then. It does because of some magic that's happening here. Technically no, the answer is no, but we'll kind of come on to that. What's actually happening is number here, I'm calling this is like a, you know, a magic number function now that number knows what to do with a CUDA jitified number function. We're calling this number function and we're giving it a NumPy array. A number is clever enough to go, you've given me an array that's on the CPU and you're asking me to do something on the GPU. So what I'm going to do is I'm going to copy the array to the GPU. I'm going to do what you've asked, and then I'm going to copy it back. And that's really helpful. It means that I can, you know, thank you for pointing that out, right? So I'm constructing these arrays on the CPU, then I'm messing with them on the GPU, and then I'm looking at them again on the CPU. And it's because Number's doing this intelligent copying for me. Now this is like super helpful in this situation, except what if I wanted to do something to my array and then do something else to my array and then do something else to my array each time? If I keep using this workflow, it's going to keep copying it, right? It's going to copy it to the GPU and back again every time I call the function, right? If I do my increment by 1, right? If I keep running this function over and over and check it, you know, we've incremented 7 times now, but that copied that array back and forth between my CPU and GPU every single time, and that's not good. So what you can also do is be explicit with that, and this is kind of, I clicked down here into memory management and data transfer, but what you can do more specifically is you can use this CUDA.toDevice and CUDA.copy to host, right, to go back again. So if I want to do something a bit more specific, let's work with this, but let's do our position array again equals that. So we've got this is our CPU, let's call this our CPU position array. Right, that looks like that. Now I can specifically say GPU pos array equals CUDA dot to device CPU position array. Okay, so I've now explicitly copied the array to the GPU, right? And it's just telling me, oh yeah, look, this is now like an ND device ND array pointer. This isn't like a thing that you can inspect. And then we can also kind of copy it back again. So we could say, let's say, what should we call this? Like returned CPU position array equals CUDA dot copy to host. Is it copy to host? I didn't even read it properly, did I? Oh no, you just call copy to host on the array. Okay, that makes sense. That's fine. So I can say that equals my GPU position array dot copy to host. There we go. And then let's have a look at it. Cool. So I made an array on the CPU. I explicitly copied it to the GPU, and I explicitly copied it back again. So if I then tried to do get position of my GPU array here, GPU pos array. So we make our CPU array again, copy it to the GPU again. I'm now going to do my function call here, and then I'm going to copy that back. We can see the numbers have been filled in, but because I'm doing each explicit step, like I'm in control of this memory management now. So I make my stuff on the CPU, I copy it to the GPU, I do stuff. I could do more function calls here, and there's no like copying or transfer, right? I'm just operating on the data that's on the GPU. And then at the end, I'm like, okay, now I want to see it. Now I want it back on my CPU because I want it in a plot, or because I want it in my notebook or whatever. So I think for now, like for the most of this like advent of code stuff, I'm gonna maybe just not bother doing memory management and just rely on Number to do this for me. Maybe things will get more complex. I don't know. But I feel like we've gone off down like a jolly exciting CUDA 101 lesson here, which is kind of what I'm intending to do, right? I want to refresh this in my own memory, and I also want to play around, but we should probably actually think about writing some code now that I can remember how to write some code. So let's call this, let's go back to, what are we doing? We're trying to calculate our expense report. Expense report, right. So our expense report was this input, wasn't it? What I'm going to do, please do feel free to shout in the chat if you can think of ways to do this. I'm just kind of thinking out loud. It's probably not going to be the best way of doing things, but I'm just trying to fit solving that problem now into like this GPU model that I've just got here. So the first thing I'm going to need is an array, right? I'm going to need to read in my file. These are like small snippets of code that I tend to just Google. So let's do numpy read file line by line. Yeah, that seems fine. Okay. So what I'm going to do, I'm going to say, will they initialize that array for me? No. So with open input.text, text as f, we get the lines, f.read lines, and then for line in lines, my array equals mp.fromString line. Oh, that's not quite what I want. Oh, I could probably just do mp.as array. My array equals mp.as array lines. Right, lines is a list now of numbers. Oh yeah, I just can't type. Let's have a look at my array. Okay. I've read all my numbers into NumPy as I read as strings, which is fine. I don't want to. Okay, I don't want to do this. Okay, that's better. I just set my dtype to float. That seems okay. So yeah, this is now going to be our. What are these numbers? Expense report. Expenses? Let's call it expenses. Expenses. My expenses is that. I've read this in. So what I want to do now is write myself a CUDA kernel that's going to work out the answer to this. So what I want to do is I'm going to call my function on each of these, and inside that function I'm then going to go over the whole list to see whether any of the other items and it add up to 2020. So let's yeah, one thing we didn't do in our little example before sorry, was like update an output array. So I might just do that here as well. So we've got expenses. Let's just, we have expenses. I'm just thinking that out loud. Right, numpy zeros from array. Right, I want like a. I want like, it is shape, isn't it? If I do expenses.shape, it's giving me 200. So if I then have my like output array equals np.zeros expenses.shape. It's going to give me like an output array that's the same shape as the input array. So I now have expenses and I have output array, and now I'm going to write some stuff. Sorting. I wonder if sorting would help. Sorting might help. So what I think one of the things I'm probably going to achieve with this is I'm brute forcing the answer basically. Maybe that's what GPUs are going to be helpful for in this context. You know, calling a same function on all of these at the same time is like extremely cheap on a GPU. But yeah, sorting would probably help from like a computer science point of view, which is maybe the point of all of this, but I'm still trying to play around a bit here. So I'm gonna carry oh, I need a drink. I'm just gonna go and get a drink. Bear with me 1 second. Right, sorry about that. Got rid of that bit of dust or whatever I inhaled. Yeah, I'm sure there's clever things you could do, but I'm going to start with like an unclever approach to doing this. So I got my input array, I got my output array. Let's write ourselves. I'm just copying the layout of this. I'm going to call this calculate 2020. And we're going to take input, and we're going to have input array and output array, and we're going to get our position. So in the input array, we're going to say, I'm going to do a for loop, which is not, for loops are generally bad, right? But I'm going to do this in here now. So for, yeah, in GPU land, you should try and avoid for loops because we can map over things in more intelligent ways. But for right now, I'm going to do a for loop. We could always tidy this up and make it even more powerful later. But I'm going to say for I in range can I do length of the expenses? Yeah, length of the expenses. And then we're going to say if input array position plus input array I equals 2020, output array position equals those times together, wasn't it? That times that. I'm also going to say if position is I, right? Because we don't want to compare it with itself. Let's just continue. So we'll skip over that, right? I'm going to say if you get to yourself, like don't compare yourself with yourself. We'll just skip forwards. But then if this plus this is 2020, then we'll update the output array with our output here, right? So that's my function. And then let's just copy my code for calling it. So this is going to be our expenses. Work out our thread size and blocks per grid. And then let's do, so we calculate 2020, then it'll be blocks per grid, threads per block. And then we're going to call it with the expenses. And did I call this output array? I did. I called it output array. And output array. Typing error. Okay. I didn't expect this to work immediately. So let's have a look. Input array. That's what I've done, I think, is I've just done the wrong brackets. That was without really reading that, but let's try again. Nope, still typing error. Okay, let's actually read the error. See what it says. No type info available for array as a callable. I thought I had just fixed. Oh no, I've done it again. So this error here, I did a few hours ago, started last year. How long have you been doing AOC? Let's check if someone else did advent of code. Yeah, so I did advent of code, like not on stream last year and probably the year before and probably the year before. I just thought it'd be fun to stream it this year. And specifically, so one of the things I do on my channel, this is Constrained Coding, where I try and do something under some constraint, right? Quite often that is, can I do something in a certain time limit? But in this situation, I'm kind of limiting myself to, I'm only allowed to use my GPU for computation. So that's what I'm trying to do here. Yeah, I'm having fun. I'm hoping people watching are having fun. Let me try. Oh, that ran. Okay, so that error that we just had there was because when we call cuda.jit on this function, number is like inspecting everything in here and doing all sorts of clever stuff. And it does like it compiles it down to LLVM bytecode if that's of interest, and then uses LLVM to compile, or like the NVIDIA flavor for the CUDA stuff of I think it uses MVCC, which is like a compiler for C++. But it can take in LLVM bytecode. So it has to do all sorts of stuff. And one of the things it has to do, because Python is not strongly typed, and in order to write CUDA code, you have to do that. It does a load of inferencing, and it's like, what type is this? What type is this? What type is this? And it kind of works everything out ahead of time. And because I'd like accidentally called this as a function, it was like very confused about what I was doing, which makes sense, right? But that was a compile time error, not a runtime error, and that's something that you're not used to in Python because there is no compile step in Python. But in number and stuff, like the compile time stuff comes up because it is compiling for us. So I've run this now. So I should now, if I have a look at my output array, have, hooray, I now have all of these things as still zeros except this one and this one, which is because the two numbers are like added to each other. Like whatever, I can't remember what position that was now, but that number plus that number is also the same as that number plus that number. So they both of these come out with the answer. What I could now do is like collapse this down to like a single value. I almost wonder if I should do it as like an empty array instead of like a zeros. Can I do that? Empty. No, that was not what I was expecting. So I guess what I want is like that. Let's just do, I can never remember NumPy that well. NumPy get non-zero elements, like that. NumPy.non-zero. So mp.non-zero. Like that. That was not what I was expecting. I call it as a method on the array, can I? Output array. Yeah, I was thinking that. I don't know NumPy that well, right? But mp.where is probably the right thing to do. If you want to throw code at me, that would be absolutely excellent. But I'm going to just read the doc string quickly. Yeah, so mp.where. I do. This is like showing how massive holes in some of my knowledge, isn't it? The output array is greater than 0 for output array. No. Oh, somebody point me at some code because I don't know what I'm doing. Oh, just a condition maybe. Yeah. Oh, can I do like output array dot where? No. Or just np dot where output array is greater than 0? No. I never remember. I'm just going to Google some things. NumPy get unique values. That was terrible Googling. Yeah, that might be. I mean, that's a helpful thing to do, right? But if I do np.unique of that, I'm curious. Oh, my output array seems to have been reset. This is why my code doesn't work. I don't know why it's giving me those numbers there, but anyway, I've got those numbers. This is why it was coming back as empty, wasn't it? This is, yeah, I think you might have been right actually. If I just do where that is greater than 0. I'm slightly confused why I'm getting that number back, but I'm expecting this number. Oh, the indices. Okay. Right. That's fine. That makes sense. Do I want to do that? Yes, that's what I want to do. Yes. Okay, and then np.unique of that is just going to give me a single number back, and then hooray! Right. That's slightly unpleasant. So that's fine. But so I've got an answer. So I could write like a function if I wanted to, which would be like for like advent of code completeness, I could write all this up as like a little function that takes in my text file. So if I do like def calculate day 01, then we'll have it like file name, because that's going to be the input. I'll call it input file name, and I'm just going to like copy all of this stuff. So say with open input file name. Oh, typing badly now. With open input file name, we get the expenses. We're going to make ourselves an output array like that. We're going to do those things. I could probably leave threads per block as like a global constant or something. And then I'm going to calculate 2020. So that would be like to set up my function. And then I'm going to return that. Okay, so then if I do calculate day 1 and it was input.text, hey, we get a number back. That was really exciting. It's such a small amount of work as well. Like my GPU dashboards are just like not doing anything, but that's fine. I have a number. It's taken me an hour to get to this point, but I think that's because we've had like a fun lesson on GPUs and I've tried to remember what on earth I'm doing. But if I put my number in and hit submit, I got a gold star. Hooray, success. That's exciting. So continue to part 2. The elves in accounting are thankful for your help. One of them even offers you a starfish coin that they have left over from past vacation. They offer you a second one if you can find 3 numbers in your expense report that meet the same criteria. Using the above example again, the 3 entries that some... oh, okay. That's fun. Okay, I did it in C# on stream. I still need to quickly write something to get the input files. Oh, do I get an auth cookie to speed up the process for tomorrow? How do you input? Yeah, I literally just copied and pasted stuff. I copied and pasted into a text file. I hadn't even thought about reading it directly from here. Doing it with a cookie makes sense, I guess, but yeah, copy paste is also like fine. So I now need to do the same kind of thing. Now this is where this is where doing things in multiple dimensions would make a lot of sense, right? I might even move on to that in like the next step, because I did this for loop, which is unpleasant. I might even, shall I do that? I'm going to try doing this in 2D, just out of curiosity, because it would make more sense. So let's come back up here. I'm going to head to writing CUDA kernels, thread positioning. I want my like absolute, right. Yeah, for last year I had code uploaded to the console, transform the input into a literal and put it in my program. It makes sense to do again. Yeah, it does. It makes a lot of sense to do that. You can almost write like a little utility library that you just use for importing other things. You just be like, you know, oh, call get input and give it, you know, you pass it the day and it goes and grabs it for you or something. Could be, you know, it could be a useful thing. I think given the amount of time it takes to copy and paste, I might, and the amount of time I'm just kind of waffling and reading documentation about number. I don't know if it's worth me implementing that. Maybe I'll do it later on a later day. I'm just gonna play around with my get positioning again, because I'm curious to see. Right, just to let me keep thinking out loud. I have to find two numbers, right? So I could use the GPU to like map that data. So let's start with like an MP zeros thing again. I wonder if I want to. I might write a little function as well. Let me just do get thread log array. I'm just gonna wrap up this bit of logic here. That is that. That is that. Just call that R, and then return threads per block. No, it's the other way around. There's no blocks per grid. Threads per block. It's just as threads. Oh, I can't type at all. How would a CUDA decorated function with other GPU libraries, say using TensorFlow, while I'm on the same GPU? So if, like, generally speaking, you can only use one thing on a GPU at a time. That's like the state of the world today. We are, you know, working on making that not true, but it's kind of, it's when you're thinking about things, especially, it's more about memory management. But if you want to run TensorFlow and run GPU kernels like this at exactly the same time, right? They're both busy using the GPU. It would work and it would be fine, but we tend to just say just do one thing at a time. But like the whole point of Rapids, right, and these kind of libraries is, like, a lot of the work that you probably do with TensorFlow is you read in some data from somewhere. Maybe you use NumPy or some other library to like transform it and do all of your like data cleaning and hyperparameter optimization and all this kind of stuff before handing over to some other library like TensorFlow or PyTorch or something. And so you do like a whole load of work on the CPU, and then you switch over to doing a whole load of work on the GPU. And the idea of Rapids is to move all of that to the GPU. So you could use cuDF, or you could use CuPy, or you could, you know, you use arrays like we're using in Number here. And so you can keep all that work on the GPU. So we have CUDA array interface. I'll Google it quickly. That's in the Number documentation. That might not be the best place to find it. Maybe there's an image. There's a slide I'm thinking of, actually. Rapids release deck. Sorry, you've taken me off on a slight tangent, but that's probably a good thing. Let's have a look at, if I click that, will it open it? Right, let me try and find a slide in here. These slides are reasonably useful, actually, especially if you want to show people Rapids, but I just want to try and see if there is a CUDA array interface slide in here. Maybe there isn't. Maybe it was at the beginning. There's a lot of slides in here. Yeah, okay, so we use arrow to like keep things in like a consistent memory format, but the main thing, I can't find it. I don't think it matters too much, but one of the yeah, yes, here it is. Hooray, sorry, right. We have two things. We have DLPack and we have CUDA array interface, which are like two different ways of interoperability. So these libraries here, CuPy, MPI4Py, MXNet, Number, PyTorch, TensorFlow, etc., they can all, you can cast one array or tensor object to another type without copying it off the GPU or doing anything like that, right? So you could load in some data with CuPy straight from disk, do some manipulation with it, and then using CUDA array interface, convert it to a TensorFlow tensor without like doing anything with the data. The data just stays exactly the same on the GPU, and then you can switch over to using TensorFlow. So things play together really nicely in terms of that. This is kind of one of the things that Rapids is trying to achieve, is this interoperability and give you like consistent workflow. So I mean, I'm doing these, you know, toy, slightly unpleasant examples here where I'm reading in data, you know, I'm like looping over things to read in data and casting them to NumPy arrays and stuff. But there's far more efficient ways to read from, you know, different files and do some cleaning. But then, you know, you could write these kind of functions that operate on your GPU array, right? You could do exactly this, right? You could read in from somewhere, do what I did before, where I like move the data manually down onto the GPU. I can't remember where I did that now. So yeah, like CUDA to device, right? So you could read in some data, copy it to the GPU, and then you could write these custom functions to do whatever you like on that array, and then you could just give that array to TensorFlow, and TensorFlow could do its thing, or PyTorch, or whatever. So yes is the answer. Is there a way to break the processing once you have a match, by the way? No. Is the short answer. I wrote my code to optimize speed to make sure I didn't do too many calculations that I don't need it, but with the GPU it probably doesn't matter much since there's so much raw power. But for later challenges you have to start doing stuff like get the solutions, don't you think? So yes, this is perhaps one of the things that maybe I need to learn more about, but as far as I'm aware, you can't break early in these things. Like the only thing I could imagine that you could do is like set a flag somewhere and inspect it in every function call to see whether like you should end or something. You could have like an extra element in the array or something that gets flipped when it finds that point. So as you're streaming through, perhaps you do that. But yeah, typically you're dealing in, like on a CPU you do one thing at a time and you can stop at any point, whereas on the GPU you can do 1,000 things at a time or 10,000 things at a time, but like those 10,000 things will happen, but they will happen at the same time. So you could do a bit of both, I guess, but yeah, I don't know. We'll find out as we go. This might be something that I learn more about myself. But yeah, good question. So I've got my little function here. I just want to do my like position array things again. So let's just do pos array equals mp.zeros. Let's put 1,000 zeros in an array, and I'm just going to do yeah, and let's have an out pos array output pos array is also that, right? I'm just laying myself out for a minute. For example here, most of the code actually deals with exiting early when possible. Curious to see what kind of issue you run into in later days. So this is kind of why I'm doing this. I'm also curious to see what kind of issues I run into, because I'm so used to thinking like, yeah, when I'm solving these kind of challenges, I'm used to thinking about CPUs. It's only like in deployment stuff really that I think about GPUs. If you didn't see, like, if you head to the like URL that's over here, I've got like a little FAQ bit, but one of the things I was kind of trying to say in that is I don't, like, this is not my domain. I'm more about helping people spin up 1,000 GPUs on AWS and perform some big calculation. I don't typically myself care about what the calculation is. There's like other people in my team and department that do, but I'm more about how do I get machines, how do I pull them together, how do I get the networking set up, how do I control, you know, it's more like sysadmin ops control type stuff, workflow type thing. So this is an opportunity for me to like learn more about how the GPUs actually work, rather than me kind of executing black box code that I don't necessarily understand. So yes, I'm excited to see what I learn from this as we go on. So let's calculate this. I'm gonna oh yeah, I want to go output array pos equals pos, which is what I did before, right? So oh yeah, thanks. It'll be good to have you around. Thanks for following. Yeah, I need to set up all of my things in my stream where it like pops up and says, yeah, I got followed or whatever. I'm still pretty new at streaming, really, I think, in the grand scheme of things. But let's do get threads per block of my position array. This will just kind of simplify that, and then let's put in the position array and the output position array. The actual input doesn't matter here, but let's do that. Invalid syntax. That's a shame. That's going to be returning a tuple. Have I not defined this? No, I haven't. Okay, that worked. That's fine. Yeah, so I've just wrapped up that little logic into here, which is helpful. So if I now have a look at my output position array, I can see all of my 1,000 numbers in here. But I could also, instead of doing that, I could do this in 2D. So I could say, yeah, I'm just trying to think about how to do this. Right, what I want to do is actually just make this smaller so I can like visualize it. I've got a 10 long array here. What I want to do is do a 10 by 10 calculation and have like 2 input numbers basically. So how do I structure that? So I want each function call, instead of it having like a position of, oh, my position is 1, it will be like, oh, I'm 1, 2 or whatever. So it will read the first item and the second item and compare them, right? Because then I think it makes it easier to move to 3D on the GPU. So if I do, it's going to be, it's probably going to be around this, isn't it? Threads per block. Maybe like that. Does the array have to be rank 2 now? As in 2D? And I think the output array probably does, but the input doesn't. Yeah, I'm confusing myself now. Does that make sense? Like, I want my output array to be like that. So yeah, oh, that's it. Yeah, that's fun. That's not what I'd intended in terms of that functionality, but I want to get my like indices. Since you just want unique combinations, just referencing the same array 3 times, making sure no indexes overlap will be the easiest. Yes, I think I see what you mean. This might be, let me have a quick look at the, I mean, yeah, in terms of like having no indexes overlap, this is kind of what I was doing before, where I was saying, you know, if this index, if my position is equal to myself, continue, right? So I would just do the same kind of thing. Yeah, so I would have that kind of thing in here as well. But I want to like move over the array in 2 dimensions. Let me come back and have a look at doing this thread positioning. So it had an example of calling a 2D increment, a 2D array. So you have blocks. Yeah, so we have to calculate this separately. This is why I didn't wrap up my functionality. And we get its position here. So yeah, let's just import math. That's fine. So threads per block is 16 by 16, and then blocks per grid is going to be those things. I'm just going to think about it slightly. I want 16 by 16 threads per block, and then blocks per grid is going to be, I kind of want it to be similar to before, right? So we had its expense size. It's funny actually, I want it to be the same right, because it's 2D, I guess I could do something like that, and then my blocks per grid is going to look like that. I reckon 13 by 13. And then if I call my function with blocks per grid, threads per block on the position array and the output array. Right, let's get rid of some of these things. Get rid of that as well. This will greatly increase your memory usage though. This doesn't scale apart. Yeah. What if they say, okay, now I have 10 combinations reduced 2020? That would not be doable in this approach, right? No, I don't think that's... You're right in some ways, in that I think the way that I'm writing this would do that, but I think I probably am just not writing this in the right way, right? Because yeah, you're kind of saying, oh, what if I want more, you know, combinations? That means this output array is going to get bigger. But actually, I don't think I want my output array to change size. Yeah, thinking about it, no, I'm going to go like that, because my input array and output array should stay the same length. What I want to do is more computation, right? So this doesn't necessarily scale beyond 3D, right? I'm just curious, because I've just never written a multi-dimensional call like this. I more just want to write a multi-dimensional call than actually because this is the right way to do it. But I feel like this is an opportunity for me to do so. So if I'm going to do my threads per block of 16 by 16 and get my that like that, and if I call it like this, I want to do grid 2 now, and this will be X pos and Y pos, and I'm just going to do that. I think I'm just curious to see what that comes out with. Output pos array. Yeah, I think that made sense in that it's got to be this X position and Y position, but the X position is just this, whereas my Y position is also what I want to do. So if I, instead of doing that, I want to say, usually with Ableton code is ask yourself, what if I 100 times some of the parts in the question, will it still work? Because that's usually why people have completely changed the solution for part 1 to do part 2. Not saying it's a bad thing, just something I've noticed. Yeah, I completely agree. I completely agree. This is definitely like AOC is quite a pure computer science problem solving thing, right? Like if you work through, like I've got this book which I quite like, right? Classic computer science problems in Python. And it's the same kind of idea, right? You're working through kind of standard common use cases, that scale, and it discusses why they don't scale. And AOC is there to kind of show how and why, and to kind of prove some of these points. Whereas I'm like taking a maybe slightly different tact here, that I want to make this stuff happen on the GPU, and I'm not like super up with the paradigm. Like I know a lot about GPUs, but not in terms of actually using them like this. So I kind of just want to play and explore and think about, oh, if I was doing this on a CPU, I would do it this way, and on a GPU, I'm doing it differently, and maybe that's good, and maybe it's bad. Like, you know, there are pros and cons to both approaches, and maybe some things vectorize. Okay. So what I want to do is here, I want to say if X position equals Y position. I'm basically, I've got rid of my for loop, haven't I? So if that equals that, I'm just gonna return, I guess. I think that's what I want to do. And then if input array X position plus output array Y position equals 2020, output array X position, I think that makes sense. A book, yeah. I think things are pretty early, right? But I'm sure that kind of stuff would be coming at some point. But yeah, for now, documentation is kind of what we have. I'm just going to say that equals that times that times that. Oh, that's fine. And then it's because I'm not calling this on the right thing. So I want to call this on my expenses. And I did this output array is the same shape. That. Okay. That's giving me a different answer. How long would you have taken to complete this in plain Python? Yeah, not long. not as long as this. This is me learning. Yeah, pure Python, this would have been nice and quick. But it wouldn't have scaled, right? This is, I guess, your point. It probably would have scaled to a level that was fine in advent of code terms, but GPUs are to like push beyond that, right? What have I done wrong? So I think it's because my input array, that's what that was. I think maybe it wasn't. And that's not worked at all. I think I'm possibly overthinking this. This would be much faster for me to do, probably. Yes. It's just me copying and pasting badly from other things. That's curious. Where does that number come from? That's the answer that I had before, right? Which is what I was kind of expecting. But those numbers are different. I'm getting some like random shrapnel that I think I'm causing. Well, they went that time. That's fun. That's not what I was expecting to happen. Something is... I don't know if this is like a result of the concurrency or something that I'm... No, I still shouldn't be doing that. I'm only checking the input array here. This is where I need to get somebody from Rapids that understands what's going on to come and help me. I want to try and pair program some of these in the future, so maybe I flail around less. Because this has taken way longer than I was hoping. But like, sometimes this is coming out with the right answer, and sometimes it is not. If input array of the X position plus input array of the Y position is 2020. If I run it multiple times, no, see, sometimes they come up. I'm getting lots of numbers now. Like slowly getting filled in with random shrapnel. This must be something to the way due to the way I've laid things out. Yeah. I definitely don't think I've done this right. But I feel like I don't understand why, right? So I've got this. This is like a 200 long array, right? And so I'm calling that number of times, which kind of makes sense, I think. 16 by 13. I'll go back. Yeah, so that is the right number of times to iterate over that. So I'm going over the array. Add more threads. I don't think so. I'm gonna try it. I don't know what. But that got worse, didn't it? Oh, and then there was none in that time. Or that time. Oh, there's lots that time. Yeah, there's definitely some like collisions going on. I'm not entirely sure why. It's got to be something to do with thread positions because those numbers aren't changing either when it happens. But make it 8 by 8. But making 8 by 8 was interesting. It's not happening now. I was running it repeatedly and nothing's going wrong. Well, I don't feel like I fully understand what I've done. Yeah, it's freaky, that's for sure. This again, this is what I'm trying to achieve though, right? Is like I don't understand why this is happening. I want to understand why this is happening. But I don't. So that's strange. But anyway, I'm getting that number out. So now let's try doing this in 3D, just to add even more insanity here. So I'm just going to do this all in one cell, I think, so I can like change it and run it kind of in one go. So let's do let's do that. Right, and then instead I'm going to make this 8 by 8 by 8. Am I going to start getting the same problems here? Maybe I will. So do this in 3D. Array output array, and that will be 3 dimensions, and we're going to have a Z position. So if any of these numbers are referring to themselves, right? So if yes, I want to do if that plus Z position equals that, and then times by the Z position. Right, that was the thing. AB, AC, AC. AB, AC, AC. You mean as in like? Yeah, okay. I think you typoed the first one, which is what confused me, right? So if that equals that, or that equals that, or that equals that, and then it'd be X, Z, or ZY, right? If any of those are equal, then skip that. Yeah. Yeah, it was the first one had a typo in. That's what threw me, right? Yeah, I could do any as well. I'm just going to do that. So that should go like that. And then I'm going to copy a 3D call. Oh. That, I think, worked, didn't it? Because it gave me some strange number. Now let's just do that just to get that out as a much better number. Sorry for all the tangents, but at what point of the entire process is at CUDA.JIT reserving one of the GPUs? I seem to remember 2 in a video SMI. It's not reserving one of the GPUs in that it is making use of one of the GPUs when I call the function, right? When I call this this line here, and also please don't apologize for tangents. This is exactly why we're doing this, right? But at this point, when I call the function, it is handing something to the GPU and asking it to call it. All of these libraries are like single GPU that I'm working with at the moment, right? They use the first GPU that they find. There's like an environment variable you can set to say which one to specifically use. But in this context, it just uses the first GPU and hands it some code to execute. And then, like, if we wanted to do multi-GPU later, we could use Dask, which is like a distribution library historically for CPUs, but also it allows you to distribute across multiple GPUs as well. So it handles chunking up things and executing it in pieces and handling like a large task graph and things. But yeah, it's at the point of calling it, we like grab the GPU, we do something on it, and we let go of it again. We are initializing some things. We are like grabbing some handles and stuff, which is why my like memory usage is not 0, and things like that. But you can call more than one thing at once. It's just that the like memory management and stuff is by default is pretty like primitive, and so it's very easy to tread on your own toes. Which is why I was saying before, like, do one thing at a time with the GPU. But there are other, there's a library called RMM, which is kind of handling virtual memory and things with GPU. So it does make all of that more possible. But I'm kind of I'm working with what I've been told of doing that. So let's come back over to here. I'm going to put that number in that box and hit submit. And hooray, I got the right answer. So my slightly flaky code, which I don't know why it was working on different grid sizes and thread sizes, and maybe I did that wrong. But I got the right answer by making a very small change in that I have no for loops at all, right? Because I'm using the GPU to do all of the what's the word? Now, how many people sold part 2 now? Where do you see that? Is that stats? Oh yeah, obviously. Okay, so 25,000 people. It's impressive how many people like didn't give up. It's about 1,000 2 or 3 hours ago. Yeah, it's a popular challenge, right? Like it's a fun thing to do. I feel like given how long this has taken of me like learning and fumbling around with GPU things, I don't know how much like. Hopefully, I'm just going to get better at doing this as I go through the month. But I think this has been fun. So I'm gonna I'll tidy up the notebook slightly maybe, but I'm just going to throw this in the Git repo. And yeah, so I think last year I think there were nearly 100,000 people that started day one, right? Yeah, I think you can you go like 2019? That's yes. Yeah, exactly, and only 3,000 made it to the end. 3% made it to the last day. It's impressive though that like most people don't stop halfway, right? Like 13,000 people got through the first bit and stopped. You're part of those 3K. Well, congratulations. I've never made it to the end. It's partly because I tend to take some time off, like right up to Christmas, right? Like and I tend to do this as like in the past we used to do this in like we used to have like an internal in like a different organization I worked in. We had an internal developer meetup group thing that met every couple of weeks. So what we would do is like whenever the like middle of December meetup was, we would do like pair programming or mob programming of trying to get through as many of the like first days as possible. So like I've never actually like sat down and worked through every single day. I'm not very good at doing it on weekends and those kind of things. So it wouldn't surprise me if I do it like until Friday and then on Monday I come in and try and do 3. Which will mean I have to get much faster at doing this. But I'm trying to stretch my brain in terms of GPU stuff, and I hope it's been interesting at least to come along on that journey this morning. So I'm going to call it a day there, I think. So thank you for sticking around and watching. I hope it's been useful. I'm going to put this video up on YouTube if you fancy watching it back. The lack of for loops is quite odd. Yes, yeah. The lack of, but for loops are slow, right? That's the thing in Python. For loops are bad. They're not your friend if you want things to go fast. So the whole point is that we can vectorize everything. That's the word I was looking for. We can vectorize everything, and then everything goes super fast, and that's what GPUs are for, right? Is vectorizing and going fast. So you're very welcome, and hopefully see you tomorrow. Thanks a lot.